the thing is that all of these experiments created blooms, phytoplankton blooms. The chlorophyll went up, and some had massive blooms, but only one experiment actually was long enough and was conducted in such a way that you could follow the phytoplankton sinking out of it. So the first tenet, the first condition of the RN hypothesis is you add RN, when you get RN, you get a growth of phytoplankton. The second condition is that phytoplankton has to sink out, take the carbon with it. So the first condition was met by all these experiments. So every one of these experiments created a phytoplankton bloom, more or less, right? Distinctly different from the surrounding water. But only EIFEX could show, because it was after 3 weeks that it happened, it was long enough. Soirée was very short. They had to leave. They created a bloom and then they had to leave after 2 weeks about, right? EisenEx was also only 3 weeks. And just as the bloom had reached its peak, we had to leave, to give the ship back. Somebody else who did something useless. Anyway. And SAGE was also out, far out. And LOHAFEX was carried out in water where there was no silicate, which I'll show you later on. So we didn't have a diatom bloom, we had another bloom of nanoflagellates. Now, this is what we had at the peak of the bloom. This is the amount of chlorophyll that came out. And MLD is the mixed layer depth, right? So you see the mixed layer depths are very different. Now, this is EIFEX, and EIFEX had the deepest mixed layer. It was 100 meters deep. And I, at that time, did not believe that you could build up a bloom at 100-meter depth, the Sverdrup story, right? That you need to have a shallow layer to build up, but here we had this huge bloom. It was actually had the highest concentration, the highest standing stock of chlorophyll. Now, so this green, chlorophyll A, is milligram per square meter, right? It's the chlorophyll in the water column, integrated, right? Whereas the pale green, the light green, is the chlorophyll in the concentration in that mixed layer. And there is confusion even amongst my colleagues about the difference between these, particularly with modelers, because the mixed layer depth varies greatly. Now look, like for instance here in seeds, this is the experiment in the subarctic Pacific. The mixed layer was very shallow, just 10 meters, right? And there they had a very high concentration in that mixed layer, right? But the total amount of chlorophyll in the square meter basis was also high, but not that high. Whereas the other extreme is EIFEX, where you had low concentrations. The maximum concentration we got was like 3.5, right? Whereas here they went into, so that's at 15 and 20 chlorophyll concentrations, very high. But if you then take the entire mixed layer, then you got a huge amount of chlorophyll, right? So the amount of carbon built up, of course, depends on the standing stock. So there's a difference between concentration and standing stock. Standing stock is then the entire standing stock to the bottom of that layer in which the chlorophyll is growing, the phytoplankton is growing. Yeah? These are the differences. So the SOFEX blooms were here. EisenEx was a short one here. And LOHAFEX, I made this before we had the LOHAFEX experiment. That was in 2009. Yeah, so I'm going to show you these 3 experiments. Now, EisenEx, EIFEX. I called it EisenEx because it was primarily a German experiment. And in honor of John Martin, he called his experiments RNX. And he died before he could appreciate that he was right, and I could tell him that. No? Yeah, so these are these 3 experiments. This was carried out in 2000, this was carried out in 2004, and this was carried out in 2009. And this is a joint Indian-German experiment. So India contributed to the funding, $2 million, and that's LOHAFEX. And LOHA is the Hindi word for iron, right? So it's LOHA fertilization experiment is the FEX, right? So EisenEx and EIFEX is European iron fertilization. We had many European, from other European countries on board. And that's why we gave it those names. Our idea from the Polarstern was that we would not just go anywhere and fertilize, just go somewhere and throw the iron in, right? but we wanted to do it in an eddy. We had done a lot of studies before that of the hydrography in the Southern Ocean, and we had come across these eddies. These are called mesoscale eddies because they're about 100 kilometers in diameter, and they arise where you have fronts. A front is where two water masses meet each other, right? And there you can have meandering. Those fronts start meandering, and then they can lead to these eddies. Now, for instance, here, you see this South Africa, you see this huge number of eddies. This is the so-called Agulhas current, which comes around South Africa from the Indian Ocean and enters the Atlantic. It brings a lot of water into the Atlantic, and in a sense, it compensates the water which is sinking in the north. The Atlantic meridional overturning circulation, right? That water is going down, and so this water is coming in to replace it. And it brings heat into the Atlantic because it's warm water. So here you have a huge number of eddies. This is a strong current. It's a compensating current. Yeah? Now, we did our experiment in this eddy. So the blue eddies are cold water eddies, and the red are warm water eddies. Now, how do you measure this? This is done with a satellite altimeter called the sea surface height deviation. And what it measures is the level of the sea surface. So the cold water eddies, they are, because that water is colder, right? The density will be the same, right? But the height will be lower because that water is colder and the volume is less for that same density. So these eddies are like dimples, right? They're depressions on the surface, right? Whereas the warm water eddies, this is warmer water, and the core of the eddy is warmer water, and they are like pimples, right? So they're elevations, and the difference is just decimeters, right? Here, this is in meters. The difference between the middle of this eddy compared to the surroundings is just about, it's between this and that, it's about 30 centimeters. I can imagine you can measure that from space. I still find it like shocking, but it's very dependable. This is always on the web. You can get all this stuff, and it's measured by the satellite, very exact, decimeters differences. Yeah, we went there, and we then actually, each of these iron fertilization experiments has so many stories with it because it's very exciting. You're never sure what you're going to get and what's going to happen, and then there are always these altercations on board about what we should do in here or not, or there or not, and so on. This goes on. So it's very interesting. And this is like a photograph of the Southern Ocean. That's Polarstern, right? And this is the surface. This is very rough. These seas are very rough. You always have strong winds, and the ship is always moving. We're all getting seasick. Our vestibular organs are having a hard time. And I told you, I get excited the other way around, but a lot of people are not happy. And the crew of Polarstern, they were always like, oh my God, we're getting another iron fertilization experiment, because they prefer to go in the ice where it's calm. Because then here, the Polarstern is in the ice. Life is easy. You don't have to worry. But here, the plates are falling down at dinner time, and yeah, it's always anyway. But then again, the mood was good, and it was really exciting. I remember when we carried out this first experiment, there was a sailor on board. I mean, most of the people didn't believe anything would happen, right? They said, this is not going to happen. There was one guy who said that, I'm going to stop smoking if this experiment, if they can show any difference from adding this iron. And he stopped smoking. Because even on deck, you could see that the water was green. When we went into the patch, it was greener than when we left the patch. So it was like, you couldn't deny that it had a big effect. All right, so how did we carry out this experiment? First of all, we had to mark the surface, right? Because we just can't go there and throw in the water and then expect things will happen. So we had a buoy like this, right? A steel buoy that was put in the water, and it had this GPS on the top, so you could follow it where it went. By that time, we had GPS, and during EisenEx, we had a plastic balloon on the top, but that was pushed by the waves, by the wind out. It was of little use. So then we had this thing made. And this is what it looked like in the water, right? This buoy. And that was supposed to be the center of the patch, because we put it in, and then the ship went around adding the iron. I'll show you how we did that, right? The iron solution. And yeah, and then we would then take samples. But the problem was that this thing didn't stay inside the patch, because it was anchored with this. Wait, what happened? Sorry. Oh yeah, no, yeah, you can see it. Sorry, I needed to mention that this thing was on the surface, and this was the drogue at 30-meter depth. This was like the sail, because this one was supposed to be independent of wind, no? And it was anchored to this at 30-meter depth. So this was marked that water mass, that water column. Yeah? Yeah, and this is what it looked like. So this thing was then circling around the eddy. This is how we take samples. This is the CTD, the conductivity, temperature, density instrument, it's called. It has water bottles. These are water bottles, and they're being tapped, right? The water bottles. And this is the CTD, when it's lowered into the water, and here it's being brought back and being tapped. And this is the iron fertilization people, the iron people, the people who measured iron. So they were, as I told you, they had a clean lab. They had a container, a clean container. This is the clean container. This is how they were dressed inside, because they had to avoid contamination. And they had special bottles that were cleaned beforehand to take the samples. So they were not taken from the standard CTD, from these here. This we used for various other parameters like chlorophyll, carbon, and things that are not susceptible to contamination. And so one reason why iron studies have been unpopular, because institutions, marine institutions, have been reluctant to invest in clean techniques. Because these clean techniques are very expensive. You have to, and they take a lot of trouble, and then they also bind a lot of people. Those people can't do other work. So people have been studying it. But I don't think we need that anymore, because we know that there's iron is missing, so we don't have to measure how low the concentration. They're low, and that's it, right? We measure all the other stuff, and that's enough, because we know if chlorophyll is higher, then there's enough iron. Right? So we don't have to measure the lowest possible concentrations of iron or iron not contaminated water. We don't need that. Okay? Yeah, so this is then what goes on in board. And then we have this is from EisenEx. Look, this is the old techniques. Huh? This is 20 years ago, more than that, 23 years ago. And here you see the CTD going down, right? And it's leaving these traces. So this green is the chlorophyll. I should have made more photographs, or got more photographs of this, just to show how it goes. So we're going down, and this is 100 meters, right? This depth here. And this is chlorophyll. And there's also temperature, salinity, right? This will be temperature. This bluish thing here will be temperature. The pink will be salinity, because the surface layer gets rainfall and so on, so it has a lower salinity and increases with depth. And then we have another instrument. Wait, let me see. There's a transmissometer as well. Which will be the transmissometer? Yeah, probably this blue is the transmissometer. Yeah, this will be the transmissometer. And this is the chlorophyll. Now, the transmissometer measures particles. It measures turbidity, how many particles there are in the water. Chlorophyll measures the fluorescence, and fluorescence is measured by fluorometer, which has a light source, which blinks. It gives a blue light, right? And this blue light is absorbed by the phytoplankton. And if that phytoplankton is healthy, then it says thank you and keeps that blue light. So you don't get much red light coming out otherwise, right? Because if you expose chlorophyll to blue light, then that light is absorbed, but that chlorophyll then gives up the excess light that it cannot use for photosynthesis, comes out as red photons. That light is then gotten rid of. So you get a red response. So you can measure the chlorophyll concentration by bombarding the chlorophyll with blue light and then reading how much red light comes out. But that depends on the physiology of the phytoplankton, how much red light comes out. So that was the FRRF, fast rapid rate fluorometer, where you bombard the phytoplankton at very short intervals with this blue light. And if that phytoplankton is healthy and photosynthesizing, then you don't get that much red light back that you get from iron-limited phytoplankton, which then is not able to use the light because it's stuck. So then you get a different signal. So you can then judge how iron-limited that water is, that phytoplankton is. Okay? Now, this is a standard fluorometer where you just measure the concentration. But then if you go in the daytime, for instance, when the phytoplankton is photosynthesizing, then you get lower values than if you go in the night or if you go at depth. Because when the phytoplankton is photosynthesizing, then the concentration of chlorophyll that you would then get from the fluorometer is lower than it actually is, right? But if you take the reading in the night, the phytoplankton has gone to sleep, so to speak, and when they get this blue light shock, most of it is then converted into red light and sent back. And so you have to be careful about this effect with fluorometers. Yeah, this is always very exciting. When the CTD goes down, then you stand over here, you have a big crowd of people watching the data coming out, right? And yeah. And then you take water samples for nutrients. No, this is an autoanalyzer that measures phosphate, nitrate, silicate, and nitrite, ammonium. Ammonium is always also critical. With ammonium, you have the problem of contamination as well. Because we are all giving off ammonium. This body odor contains ammonium. And so the ammonium measurements are not good with autoanalyzers, but nowadays they are. Besides, they're pretty low. Whereas with nitrate and phosphate, you get very good data. I'll show you later on the data. But this is how we measure that. And here you measure particulates. These are filtration devices where you then put filters into below this funnel. You unscrew the film, put a filter in and close it, and then you invert a bottle. You take a water sample and invert it, and then it's filtered onto this filter, and then on that filter you can measure chlorophyll directly, and then you get a dependable chlorophyll concentration. Whereas the in situ chlorophyll measurements taken with profilers are always dicey because it depends on the physiology of the phytoplankton. Whereas if you have it on a filter, then you get the chlorophyll that's there. You extract that chlorophyll and measure the concentration. But you also measure so many other parameters like carbon and nitrogen, the CHN analyzers that measure the carbon concentration and the nitrogen, organic carbon, organic nitrogen. And then, of course, you also measure CO2 in water samples separately with analyzers. You measure CO2, you measure dissolved inorganic carbon, alkalinity, and so many other parameters, whichever you want. No? And then you also measure zooplankton with nets. No? These are multinets. No? There are, I think, 3 or 4 nets, I think, that open at different times. Right? You put the net down, and down to the bottom, and then you pull it up. And then you pull it up, let's say, you take it down to, let's say, 500 meters, then you pull it up to 200 meters and close that net. Then you have the 500 to 200. And then at 200, you open another net, and that you take that to 150, for instance, and you get that 50-meter concentration of zooplankton, the population of zooplankton, then another 50 meters, and then another, and so on. So you get the distribution of the zooplankton with this multi-net. And we are assuming that this is the opening of the net, that the zooplankton is not escaping, but it is. No, I told you the scopopods, when they sense something coming, they sense the wire coming up, so they jump out of the way. So these nets will always underestimate the zooplankton because you cannot avoid the escape. And how much that is controversial, because the people who only use nets, of course, they will argue that it's okay, because otherwise their data is questioned. And otherwise, you can also always be uncertain how good the zooplankton data are, the quantitative. Now you saw how active these zooplankton are, the copepods. So one way around that is to have an instrument that measures the zooplankton in front of a device which uses light, for instance, right? Which looks at the reflection of light. But if they're transparent, then again, actually measuring zooplankton quantitatively is a big problem. And it hasn't been solved yet. I'm still unhappy with the results we have up to now, because I think they are underestimates, that there is always more zooplankton there. Yeah, anyway, so these are the measuring. These are salps, I told you, the red dots, right? And you see how transparent they are. Actually, in these samples, they have already been here for some time. But if the net catch is very fresh, you only see the red dots. You don't see the animals at all. But of course, here there are also copepods in between. Huh? So these are the zooplankton samples that you get from these nets. Yeah, because you want to know the response of the entire ecosystem.
Yeah. So we knew the balloon because the phytoplankton were rising, but why do we need to know the zooplankton, their amount?
I'll show you what we found in the zooplankton. The zooplankton also responded. Yeah, because the phytoplankton and zooplankton are geared. The zooplankton, the copepods, of course, they have life cycles of a year, 2 years, right? Or some smaller ones, months, right? So they take longer. But you can see whether they are laying eggs or not. They start making eggs or not. And that's what we could show. Yeah, so this is the iron. No? This is ferrous sulfate. And the ferrous sulfate is a waste product of very many industries. It's produced, about 400,000 tons of ferrous sulfate is produced by a factory opposite the Alfred Wegener Institute. It's called the Kronos Titan factory. It's a titanium factory. They have titanium ores that when they're treated, to extract the titanium, you have as a waste product, you get sulfate. And sulfate is always difficult to get rid of because it's sulfuric acid, right? So they combine that with iron because iron is the cheapest cation, and they produce ferrous sulfate. And that ferrous sulfate can be taken care of for whatever, right? But it's a waste product, actually. So now they're using it, for instance, for lawns. So I have a bucket in my room of ferrous sulfate for putting on the lawn. Actually, it's used to kill moss. It's strange because what happens if you put ferrous sulfate on your lawn, the moss go wild. They grow like crazy. And you know that mosses don't have roots, deep roots. So then they grow so fast that they come out of the grass and then you can rake them out, get rid of them by overgrowth. So that's one way to get rid of the stuff, right? So they sell it quite cheap, and you can get a bucket and you add 50 grams per square meter of this ferrous sulfate. And in the ocean, we add like a few milligrams per square meter, right? Because that's enough to fertilize the entire water column. Right? So this ferrous sulfate, they would give us for free, but we paid 1,000 euros or something like that for 10 tons of ferrous sulfate. So they come in these bags. So we then take the bags, cut them open, and put them in this funnel. And this is seawater, no? With seawater, and then there's some acid. We have to add acid as well, hydrochloric acid, because otherwise that ferrous sulfate becomes rust very quickly. It gets into contact with oxygen, becomes red, and it would then precipitate out, and you would have this rust, mud made out of rust, so to speak. So to prevent that from happening, you have to add the acid. It's a very weak acid, it's hydrochloric acid, but the pH is like just 2 or something. And then that solution, that iron solution, can be released to the ocean. Right? And that's done this way. So we have these tanks on board, 10 cubic meter tanks, and they're being filled. This is the pipe coming from that funnel. No? This is the iron pipe. So we did that in shifts. So when we were fertilizing, then we had 3 people who would then be doing this, adding the iron, the hydrochloric acid, and filling up these tanks. And then when a tank was full, it was released. And this is the outlet pipe. See, this here This is garden pipes, right? This is the outlet pipe going into the sea. Now it's going here overboard at the back of the ship, and you can see it here. The pipe. So this is how we added the iron to the water. And the ship was going around in circles. So this is how we did it in EisenEx. No? The initial was here. And then this is the currents. No? Here you can see the eddy, right? These are the current strengths, and this is done with an ADCP. The ADCP is an instrument that measures with a Doppler effect. It sends acoustic signals down, and the reflection of that acoustic signal is always a little bit later, and the faster the particle is going, you get the Doppler effect. You know the Doppler effect? When you're standing somewhere and there's a car, an ambulance going past, right? So when the ambulance is approaching, it sounds differently to when it reaches you and then when it goes away. Because when it's going away, when it's coming, and when it's going. Because it takes time. There's a sound, the speed of sound. So that's a Doppler effect. So we use that also, and you can measure the speed of that particle with this Doppler effect. And with that, you can measure the current, the flow of the currents. And that's given here, the length of the arrow. No? So here you have strong currents coming down like that, right? And here you can see them going up again. So this was the eddy. And in the core of the eddy made the patch. And these are patches like over time, right? Here's the SF6. These are the SF6 measurements that were made by Andy Watson and his group from the UK who did this. And this is the first patch, this is the second patch, the second time, right? A week later, this is the 2 weeks later, and this is 3 weeks later. This is the patch at the end of the experiment when we had to leave, the yellow. And then how do we find the patch? This is what I mentioned to you, the SF6, the FRRF. You have an inlet of seawater flowing into the ship, and we are measuring then with this FRRF the response of the phytoplankton. So we came from here, right? Because we have to take samples outside the patch as well, to prove that this is the patch, and the outside samples are the control. So you come, and this blue shows you the FV over FM. That is a ratio that gives you the physiological adaptation of the phytoplankton, the photosynthesis response of the phytoplankton. So if it's low, that means they are iron limited and they're not growing fast. And if it's high, that's the highest F value you can get. That means they're photosynthesizing. So we came with the ship here, and then we went south, no? Because that's where this buoy was, and then you get a higher value. And then you say, okay, let's see how fast this goes. And you go in this direction, and you're out of the patch. And then we go back again, and then we're in the patch. No? So here in the patch. And then from here we come again and do this kind of a back and forth, right? And that here, this is where the patch is, here. And then when you're here, the patch is over. This is the boundary of the patch. Then you turn the ship and you go back into where it was the highest concentrations, where you had the highest response. And then we made the station over there. And then we took the samples there. So this is how you run these experiments. And of course, each station, when you're taking samples, it lasts for hours because you have all these different instruments going in, right? You have the CTD going down, and you don't want to go too deep because if you go too deep, it takes more time. You want to have the next station, and you want to stay in the patch. And if the patch is small, then you can also miss the patch, or you can take a sampling where you drift outside the patch and so on, right? So you can imagine the area. Now it's like about a few kilometers only, the patch, and in this case, because we only added a few tons of iron. So that was a problem. But here you see so we had an online FRRF, but we also had a profiling FRRF, and this is the profile. So here, this is day 0. This is before adding the iron. This is day 0. And then we had to do the fertilization. And then we came back and ran this station, and there you already see the response. right? And then on 2 days, 4 days, 6 days, and so on. So after 21 days, you could see that that patch was going like booming, right? Growing like hell. And this is outside, because we also always had to leave the patch to take the outside station and then come back in again. And here you can see that it's only the deep phytoplankton that were slightly not physiologically affected, but the surface layer they had very low values. They were suffering from iron limitation. And here you see how it built up. And these are now water samples. So this is the phytoplankton. These are diatoms before adding the iron. And the cells, the cells of this corythral inermi are more or less empty, right? And you have a few pseudonychia. This is a diatom, pseudonychia, the needle shape, right? And this is inside the patch after 3 weeks, how the diatoms built up. And this is pseudonychia, and this is Fragilariopsis kerguelensis. This is that heavy silicified diatom that then grew like crazy. So these were 2 species from that bloom. Now there were other species, like here, this is the Fragilariopsis kerguelensis. This is the famous one that has those very thick frustules that are very difficult to break. Remember I showed you those studies that we carried out on them? And they have very thick shells. You can see, look, you can see the frustules, right? These, what you see here as dots, these are ribs, right? Inside the supportive ribs. And if you compare that with pseudonychia, then you see pseudonychia has smooth, thin shells. So it has much less silica per carbon, both of them, than this one, right? And here's another thick-shelled species, Thalassionema nichioides, and these 2 have in common that they grew inside the patch. This went up to 150 milligram carbon, and this went up to 80, but then it stopped growth. Here you start understanding the ecology of these species. Not all species want to grow like crazy all the time. They grow and then they stop, and then others don't grow at all. And so we studied the phytoplankton in great detail, which was not done to the same extent in other experiments, except for the Japanese ones. In the seeds experiments were Japanese. They studied the species, but other institutions did not do that same study with the thoroughness with which we did it. So these are some of the species, and the total amount of carbon that was built up in this EisenEx bloom was a few grams, of which 1/3 was the pseudonychia. But we had to terminate it after 3 weeks because we only had that much ship time. And the day when we stopped taking samples and had to go back to port was a really sad day for me. Because it would have had such an impact on the planet, if you wish. If you had continued studying this and built up the bloom to its peak and then had this massive sedimentation, which I'm 100% sure happened. Right? And we don't have satellite data for it because it was very cloudy in that period, so we don't know, we can't tell from satellite what happened afterwards. Anyway, so that definitely would have been the case here. The soiree experiment, the 2-week experiment I told you about, there, 1 month later, they still could see the bloom on a satellite image. They had a lucky day where the Southern Ocean is very cloudy. So there was a day where you got a good picture, and there you could still see the bloom was there. And I'm sure that bloom was primarily due to this species, to this Fragilariopsis, because this is a persistent species. It doesn't sink. It stays in the surface and then it just sheds its frustules, the ones that are then grazed or it just dies. I showed you those chains, do you remember, with a lot of empty cells in it? We don't know why they died. But we need to have much more information on the biology of these dominant species, which we don't have because we are not doing that kind of targeted research. So if we were to carry out more iron fertilization experiments, we would learn so much more about the biology of the Southern Ocean. And move on to the next experiment, which was successful because it was longer, and that was EIFEX. Here again, you see these, and in South Africa here, This is the Agulhas current. And this, we targeted this eddy first. So we went there, but then I liked this eddy better. From the distance you could see it was more stable. It was stabilized by 2 warm water eddies, whereas this one was being sucked out. You can see it was leaving out. But still, the oceanographers on board, they decided we want to go to that one. This would have been even better. But anyway, we went to this one, and then we fertilized it. And this is what it looks like. So we left Cape Town and headed for this one. Yeah? We went south. No, that was the eddy. And then what happened is that we missed the eddy. Because with the ADCP, you can measure the current speeds. So you know that you're in an eddy when you have reverse currents going in the other direction, right? So we went down this way and all the currents were in this direction. So then we stopped the ship and went this way and then searched for the eddy. Then we found the eddy over here, right? But after doing all this kind of searching around, and it was messy and I didn't like it, but we decided to make a fertilization there. And then I said, after that we're going, I was the chief scientist. So I said, after that we're going to go to this eddy, right? And there was huge opposition. They didn't like the idea, no, we should stay here and so on. But I knew that this eddy is going to collapse. So after we fertilized it, we went then to this eddy. But on the way, a huge storm came, right? So we had to go north to avoid the storm because the storm went through this belt. And after the storm had passed, then we went then in this direction. The storm went here. So we went in this direction, and then we came south again and went right through the middle of the eddy and then stayed there because it was a perfect eddy. And this is how we did the fertilization, right? We made a preliminary map of the eddy. You search around, where's the eddy? And then we went and fertilized. This is what the fertilization looked like. It was Lagrangian. That means we were following the flow. It was not geographic. You don't make a dot and then you just go around it. But we put out this buoy, the one I showed you, the yellow thing, right? And went around it and increased the distance to that buoy. Now we made a spiral around it, releasing this iron which I showed you. How we did it. And then after that, we went and we did a matrix to get the overview of the region and let the eddy incubate. And while we were running this, if we cut the fertilized water, we had moved out because you could see instantly the response. Yeah, and after that was over, then we went and did this, I forget the way, Matratze in German, right? We did up and down and measured the overall background, and then we went back into the eddy and did the measurements one after the other. And yeah, so this, when we went up here, I almost had a mutiny because almost everybody was against leaving this eddy. And it was lucky because this eddy collapsed after the storm. It dispersed. It was, again, you need luck, right? So here we had good luck. This is a storm. No? This is what it looks like when you get into really stormy weather. This, when work is stopped because you can't go on deck, it's too dangerous, you get washed away. But what happened here, in the meantime, there was a person called Russ George who ran an experiment without asking anybody. He went and got money from funders who were going to start a carbon market, carbon credit market, to do fertilization experiments and then get money for sinking carbon, sequestration. But that market has never been really clear. But he was wanted to be a pioneer. And he was attacked, rightly so, because it was not a scientific experiment. He was attacked by NGOs and so on, non-governmental organizations. Greenpeace attacked him and the World Wildlife Fund and so on. So he had to break off the experiment. But it got a lot of coverage, a lot of attention. And we had been planning this experiment for years before this guy appeared, right? And when we then said that we are carrying out this experiment, we had announced it. It was, as a matter of fact, there was a joint agreement between the Indian and German governments, and the contract was signed in front of Angela Merkel. She went to India on a visit, and there this contract for LOHAFEX was signed by the research ministers of both countries. So it was above board, it was a clear cut, there was no restrictions on it at that time, right? But when we set sail, when we left Cape Town, there was one NGO from a group called the ETC, and this person in Cape Town sent a press release to the newspapers, the local newspapers, that the rogue ship slept out of town. So the captain almost had a heart attack when he read that in the morning. The agent faxed him this newspaper headline from Cape Town. And then we had this storm, right? This is from the ETC group who are opposing geoengineering, right? That geoengineering is bad, and that it leads to all these things, no? Horrible things. And then this is the press, the media at the time. These are the headlines when just a day or two after we left Cape Town and were going to the place where we wanted to carry out the experiment. No? Here. German geoengineers show iron will to defy global UN moratorium. They were claiming that there was such a thing as a UN moratorium. Moratorium means stopping, forbidding something of iron fertilization. And that was wrong. It was not true at all. No? It was totally misunderstood. Anyway, so there was all this stuff. Times of India wrote, the Antarctic Mission runs into protest, and Umweltschützer behindern Algen Großversuch. No, this was here. And so on. Süddeutsche, no? Ministerstreit. Anyway, it was a big affair. And the ETC group actually put out this poster that adding iron to the ocean is going to kill fish. They know nothing about iron fertilization, but they were opposed. And this opposition is still out there. So what happened is that for 2 weeks, we were not allowed to do anything, right? So we were fiddling around, waiting to get permission. And then the RV then organized lawyers, international lawyers, to look at this contracts, whether there was this moratorium existed or not, and so on and so forth. So there was a big hullabaloo about this whole thing. And then we got the permission. Angela Merkel personally then at that time said, okay, we can go. And of course the Indian government as well, right? So then we carried out the experiment. But see, this is the kind of response we got. Can you imagine how nerve-wracking it was? There's an article in Nature on this, no? So if you look on the web, you can see it, no? And this just shows you the attitude. This is why you haven't heard much about iron fertilization experiments, because people think it might be bad. And the reason why they think it might be harmful is because of this pseudonitia, this domoic acid. It's a invented story. Okay? Anyway, but these people were attacked. There were other people with whom we had no connection who attacked them. Says, why are you stopping a valuable scientific experiment? So then we were given the green light and we went ahead with the experiment. Now, yeah, so what I see, this is actually, you know what friendly fire means? When people from your side shoot you by accident, it's called friendly fire. That used to happen in the Iraq war, when aeroplanes were called and then they went and shot their own troops instead of the so-called enemy at the time. Anyway, so that's why I say that all these nature conservation groups that attack iron fertilization, this is friendly fire because they don't understand what we are doing. Yeah? So we need to educate the public and make clear what the alternatives are. Doing nothing is the worst option. Melting of the Arctic summer sea ice could be reduced by local cooling of the atmosphere. We could do things to slow down global warming, and we could stop global warming by taking CO2 out. But that's huge, the amount of CO2 we have to take out. Right? It's the same amount as is in the biosphere, the entire biosphere. It's a challenge. But if you don't meet the challenge, you say it's too much. That's not, the Homo sapiens has always said we'll do it. We have to. And now look at what is at stake. Even the deep ocean is at stake. The benthos depends on us. Now, this is one of the papers that came out of LOHAFEX. Iron fertilization enhanced net community production. Production went up, but downward particle flux was not enhanced by iron fertilization. So iron fertilization in the absence of silica is not going to work. But in the presence of silica, like in EIFEX, you will get big blooms that will sink out. This is another technique that we used, on LOHAFEX and also in the other experiments, this is the thorium-uranium ratio. Uranium is, I told you, is present in the water, dissolved, and the radioactive isotope, U-238, it breaks down into thorium. And uranium itself is highly soluble, but thorium is not. Thorium attaches to particles, right? So by looking at the uranium-thorium ratio, it should be constant if everything else is constant, then you have a certain ratio. But if you have a loss of thorium, that means particles have sunk out, okay? And that you can see over here. Now, it's in depletion of the thorium. You measure the thorium deficiency, how much thorium is lost. And this should be the kind of normal relationship between the two isotopes. And you see there was no change. That means there was very little loss of particles during LOHAFEX, this technique. Whereas in EIFEX, we had a massive loss. The thorium values went really deep down. They were the lowest ever measured in the Southern Ocean during EIFEX. Yeah, this is the crew that carried out LOHAFEX. And the companions we had on this 7-8 weeks was this albatross. This is the giant albatross flying around the ship. Of course, we didn't feed it. And then we also had a seal. We were in the middle of the ocean, and the seal comes up. And comes swimming. And what the seal liked, why it liked the ship, was because we had these bow thrusters. Bow thrusters are propellers in the front of the ship to keep the ship in position. So every time that was switched on, the seal would go wild. Here's the seal, right? And this is the bow thruster pushing water out. And it would swim against that, right? It was like, wow, this is great. Like in a Jahrmarkt, in a carnival or something. And then when it was switched off, the seal would go, oh, what happened?